And the first thing we're going to look at here is the solubility, which gives us an idea of the maximum amount of solute that can dissolve in a given amount of solvent, and then I'm going to put in parentheses, at a specified temperature. Because as we'll see in a second, solubility is very much temperature dependent, whether we're looking at solid solutes or gas solutes. So this comparison of the amount of solute dissolving in a given amount of solvent is often represented this way, right? So I mentioned, water tends to be the universal solvent. We're going to see that over and over again. So it's represented in terms of grams of solute that can dissolve in every 100 grams of our water. Those are the typical units that you'll see throughout your textbook and other places. So based on how much solute you have in a given solution, we can classify a solution as belonging to one of three categories, either unsaturated, saturated, or in some cases, supersaturated solutions. So in an unsaturated solution, there is less than the maximum amount of solute dissolved. So what that means is if you added some more solute to the solution and you stirred it up, it will dissolve in there because there's room to add more to it. So unsaturated, less than the maximum amount. You can think of, maybe a couple analogies. If you have a sponge, right, a dry sponge, and you add a little bit of water to it, just a little bit, it'll absorb it. Right? So we can say the sponge then is unsaturated because if you add some more water to it, it will absorb it some more. And we can keep adding water to it until we get to the point where it can't hold anymore. Right? Maybe an analogy might be more applicable. Instead of a sponge, well, you can think of your brain as a sponge, I guess. So if you think you're studying for an exam, right, and we're all in that boat, I think, and you start studying, and at the beginning, you have room in your brain to put some stuff in there. And you put a little bit, and you can keep putting more because it's unsaturated at the beginning, until you get to the point where your brain cannot hold any more information. Right? Maybe we're at that point. Maybe. But hopefully you're still unsaturated, and there's room for more stuff in there. So any extra solvent, solute, will dissolve in the solution. Right? Unsaturated, room for more. In a saturated solution, this one is going to contain the maximum amount of solute in it. So if you added any more solute, so adding more solute, let me rephrase that, I'm sorry, erase that. Say any added solute will not dissolve. So if you have a salt water solution and you've reached the solubility limit on it, if you added any more salt to it and you stirred it up, the salt's not going to dissolve, it's going to go to the bottom. Right? Similarly, if you have your saturated sponge and you added more water to it, it's just going to go right through, or it's just going to fall off. It may go in, but it'll force other water out of it. right? There's not room for any more. Maybe similarly, if you're studying and you get to the point where your brain is saturated and you try to put some more stuff in, either through your ears or eyes or whatever, maybe some other stuff has to leave, right? There's a limit that you can reach in terms of not just your brain, but sponges, but also solutions behave the same way in terms of how much of the solute they can actually accommodate.
Is that why you float in those float pods, isolation tank things?
I'm not familiar with the float pods. You're going to have to
It's
explain
like
that.
super saturated with salt so much that you float in it, so you just get in, it's good for your back and everything.
Yeah, so I see what you're saying. So, I mean, there are natural places, like the Dead Sea, for instance, that are really, really salty, right? That has to do also with the density of the sea in that case, right? So less dense things float on things that are denser. So that's the idea behind that, right? So you have to think about floating. You just lay down and let the currents take you where they may. All right, so let's take a look. We're saying here at 40 degrees Celsius, the solubility of KBr. So what's KBr? What's the name of KBr? Potassium, so K is potassium, Br is bromide, is 80 grams for every 100 grams of water. Right? So what this means then, at that temperature, we can dissolve 80 grams of KBr for every 100 grams of H2O. Right? That's what the solubility is telling us. That's a maximum amount of that solute we can dissolve in 100 grams of water. So based on that ratio, can we determine whether these, we'll just take a look at a couple of them, are saturated or unsaturated? So here we have 60 grams of KBr to 100 grams of water. Does that contain the maximum amount or less than the maximum amount? Less than, right? So that would be an unsaturated solution, meaning there is room to add more. You can add, specifically in this case, 20 more grams for you to completely saturate the H2O. What about B? 200 grams of KBr added to 200 grams of water. So 200 grams of KBr to 200 grams of water. This is the same thing as saying 100 grams of KBr for every 100 grams of H2O. Right? So in this case, we have more than we've exceeded our solubility, so then this would be a saturated solution. Right? That extra 20 grams will just sit there in the bottom of the container, whatever that container happens to be. So we can qualitatively describe our different types of solutions, but in more concrete cases, we can actually put some numbers and quantify the relationships and to compare our solutions to others. So there's a third type of a solution that you may encounter, which is very different than the other two, and this is called a supersaturated solution. And a supersaturated solution, first of all, it's rare. You don't see it very often. And it's unstable. And not unstable from the sense that it's going to explode, but unstable from a different perspective. I'll explain that here in a second. So supersaturated means that it temporarily contains more dissolved solute than it should. Okay, and there are special conditions that are needed for that. Oftentimes it involves changing the temperature of your solution. So for example, if you've made like candy and stuff at home, right, where you have a bunch of sugar dissolved in water, and then you can adjust the temperature, maybe cool it down a little bit, and then you see whatever sort of crystals start to form. What you're actually doing there is making some supersaturated solutions and then disturbing that solution to make it or to cause those extra solute particles to come out. So it's rare, it's unstable, it temporarily, for a short period of time, it's going to contain more dissolved solute than it should. Okay, and if disturbed, the solute comes out of the solution as a solid, right? And we don't, in lab, there's actually a good experiment we could do in lab to illustrate this, which ends up being quite dramatic, but we're not doing that one this semester. My point here is for the supersaturated solution, it's a temporary situation where you have an unstable solution. And when I say disturbing it, right, all that can involve is just a speck of dust falling into the solution. And it causes all of that solid that's in there to actually precipitate out, meaning it forms a solid in that solution. In some cases, it can look extremely, the process can look very dramatic. So if you've ever seen, not pictures, but if you ever watched the Superman movies, anyone. So where he goes to his fortress of solitude up at the North Pole or whatever, and you have these huge crystals of ice, it's kind of like that you'll see in your solution, but in a very, very small case. And you can actually see them forming, like growing, like crystals in there. So supersaturated, unstable, temporarily holds more solute than it should, and then if you disturb it, it comes out of the solution as a solid, right? Just like temporarily when you study for an exam, right, you may be able to stuff some more stuff in your brain than you should, but then you may become a little unstable as a result of that, right? And you need to get rid of some stuff to reestablish your equilibrium. Okay, so those are our three types of solutions that we can see based on the amount of solute dissolved in it. The next thing that we're going to address is that second part of when we defined our solubility, we said it was the maximum amount of solute that can dissolve in a given amount of solvent at a specified temperature. Right? So you have to specify the temperature because solubility is temperature dependent. So we can say for solid solutes, as the temperature increases, the solubility also increases. Monday lab people, what do you call that type of a relationship? Direct or inverse? Direct. This is a direct relationship. Wednesday people, you're going to see this tonight, a bunch of them. So if you take a look at our graph here on the right side, you can actually see how the solubility changes as a function of temperature. Right? So on the x-axis we have increase in temperature, on the y-axis we have solubility. And these are all solid solutes. So if you look at one of these that you're familiar with, sodium chloride, NaCl, as you increase the temperature, you can see the solubility kind of increases a little bit, right? It slopes upwards. It's not a dramatic slope, but it is a slope upwards. Some of the other substances, so for instance, like glucose, right? As you increase the temperature, the solubility goes up almost on a logarithmic scale, right? Exponentially. And glucose is a type of sugar. And you probably know this from experience. You have a hot tea or a hot coffee versus cold tea or cold coffee. Which one can you dissolve more sugar in? The hot one, right? So as you increase the temperature, you actually allow more room for the solute to dissolve. Or you can dissolve more solute in something hot versus something cold. And that's for your solid solutes. The case is different for your gas solutes. So for gas solutes, and I'll just say, for example, CO2, like carbon dioxide, as the temperature goes up, the solubility actually decreases. And that would be an example of an inverse relationship. Right? Because the solubility decreases, what that means is that the gas will leave the solution. Right? We talked about at the beginning that solutions, they're often liquids, right? And you can have solid dissolved in liquids. Sometimes you can have gases dissolved in liquids. So what we're saying here is, for a gas dissolved in liquid solution, when you increase the temp, the solubility of that gas decreases. So for example, if you buy a can of soda or something in the morning, if that's your preferred drink in the morning, right, and you're in your car, you open it, you take a drink, and then you let your can of soda or your bottle of soda sit in the car for the whole day, right? Sitting out in the hot sun. When you come back in the afternoon or the evening and you take a drink, right, how does it taste? It tastes flat. So describe that. When you say flat, not carbonated, right? The tingliness goes away. So why is that? What's responsible for the tingliness or the carbonation? The CO2, right? The carbon dioxide in there, the bubbles that you see, that's responsible for the tanginess or the tingly thing of the soda. So as it's exposed to the sun the whole day, the temperature is going up. And as the temperature increases, the solubility of the gas decreases. And that means the gas will leave the solution. So there's less of the CO2 dissolved. So it tastes flat. How else did you say it tasted? Sugary. It tasted sweeter than it did at the beginning. Well, assuming nobody came and added sugar to your thing, why does it, there's no sugar genie in your car, right? Well, maybe there is, but why does it taste sweeter?
Maybe because, I don't know.
So the carbon dioxide in there, right, makes it taste a little acidic, because you actually make a little acid in there. So when the carbon dioxide leaves, you don't have as much of that acid taste. So some of the background flavors actually become more prominent, so you actually taste the sugar a lot easier, or better, or more efficiently than the other flavors. So that's what can happen on a small scale. On a bigger scale, right, when you change the temperature of large bodies of water, for instance, like lakes and oceans, you also decrease the solubility of gases in there. Right? So if you have a lake, for instance, and the temperature of the lake goes up, well, then the solubility of the gases in the lake decreases. The gases are going to leave. And if there are things living in the lake that depend on oxygen, for instance, that can be a problem. Right? So you decrease the solubility of those important gases. You essentially, lower the condition, or you minimize, or you make the environment less conducive to support life. All right. So the next thing that we're going to take a look at is how the solubility of a gas is influenced by pressure. And this is an example of another gas law. So the Monday people, we looked at, I don't know how many, 5 or 6 gas laws in lab. This is another one that's sort of hiding out in plain sight. This is called Henry's law, and it has to do with how the solubility of a gas is influenced by the pressure. All right, so Henry's law is pretty simple. It says that the solubility of a gas in a liquid is directly proportional to its pressure above the liquid. So in other words, right, if we say something is directly proportional, that means if we increase the pressure of the gas, the solubility will increase as well. That means we can dissolve more gas in that solution. And then the opposite would be true, right? If you lower the pressure, then the solubility of the gas will decrease, meaning the gas will actually leave the solution. Right? If you go back to the example of your favorite carbonated beverage, right? Whether it's a diet something or a Coca-Cola or a Pepsi or a Dr. Pepper, or whether it's something a little bit more stiff, right? When you open it, whatever, you pop the lid and you hear the psh, and you see the bubbles coming up, right? When you open the can, what are you doing to the pressure? You're releasing it, meaning you're lowering the pressure, right? So as the pressure goes down, the solubility of the gas decreases, meaning it leaves the solution, becomes less soluble in it. And that's what you see as the bubbles. And that's what you hear as the sound when you open it. So that's Henry's law, right? Every time you open a can of something, carbonated beverage, you're using Henry's law. Okay, the last section here in this subcategory is devoted to looking at whether or not an ionic substance will dissolve in water in the first place. So when we looked at how solutions form, we said that for an ionic solid or for an ionic substance, it dissolves as individual ions, right? It breaks apart into ions. But not all ionic compounds are soluble in water. Some do not dissolve in H2O, and that's actually a good thing, that they don't dissolve. So how do we know whether something dissolves in water or not? Well, add some water to it, see if it dissolves, right? That's a pretty simple experiment you can do. Thankfully, people have done that for all different combinations of ionic compounds, and they have tabulated their results into what are known as solubility rules or solubility tables. So just based on the types of ions that we have in an ionic compound, we can actually predict whether or not it will dissolve in water. Okay? So I think this is straight from your textbook. Yeah, table 9.7 from your textbook. It's a simplified version of a solubility table. All we're going to be looking at here is to find the ions in our substance and see whether or not it matches up to our table. So let's take a look at the thing that we focused on a little bit already, sodium chloride. So sodium chloride contains what ions in it?
Sodium plus with a positive charge, chloride with a negative.
So sodium chloride, as the name suggests, contains sodium, Na+, and we have chloride, Cl-. Right, so all we're doing is now looking for those ions on our table. And if we find them on the table, that tells us that that thing, whatever it is going to be soluble. We find sodium on here, there it is. So that means any compound with sodium in it will be soluble in water. Sodium chloride has it. So it will be. If you look for the chloride, you can see chloride is on here as well, and it's not an exception, so that means that sodium chloride is soluble in H2O, and you already knew that, right, from your own personal experience. This is just confirming your observations, right? You've been seeing what you're supposed to be seeing when you add salt to water. It's supposed to dissolve. So, ionic compounds that contain at least one of these ions on the table should be soluble in water. If you don't see the ions on this table, then we're going to assume that they are not soluble. So let's apply those rules to some of these combinations down here. So let's first of all take a look at K2S. and look at the table to predict whether the K2S, which is potassium sulfide, if that's soluble in water or not. Okay, so raise your hand if you think it's soluble. Why is it? Go ahead. Why is it soluble? What is on the chart? Potassium, yeah, K plus, right here, right there, right? And potassium sulfide contains the potassium ion in it. Soluble, that's how you use the chart. It's not that difficult. Just locate the ions. But you have to figure out what are the ions that make up the compound, right? That's the challenging part of it. And then you can use the table. So yes, this will be soluble in water because K plus is present. What about CaNO3? Raise your hand. Should it be soluble or insoluble? CaNO3. No, you've already gone. Okay, go again. All right. So let's see. So you're saying yes.
Can you zoom in?
So it's soluble, yes, because of the presence of which ion? So let me just write the formula again. It was calcium nitrate, CaNO3. 2. So which ion on this chart will tell you that it's soluble? The nitrate, right? That's anything with nitrate in it is soluble, no exceptions. So the NO3 there is telling us that calcium nitrate is going to be soluble in H2O, right? Actually, anything with nitrate is always soluble. Let's take a look at the last one, AlPO4. 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 Yes.
No, why? Okay.
No, I didn't hear what you said. What did you say?
Oh, I said no.
No, okay. No. Why? It's not. What's not on the chart? So I'm trying really hard to listen to what you're saying, but I can't hear anything.
No, because the aluminum is not on the chart.
Aluminum is not on the chart. Is aluminum the only thing in our formula?
PO4.
PO4. What's the name of PO4? Phosphate. Right? So Al3O4, I'm sorry, Al3 or the phosphate, we don't see that on the chart, right? Neither of them are on here. You don't see them insoluble. Right? So this would be insoluble in H2O. So nope. So not ions, not on chart.
You have to memorize that chart first.
No. No, but as you're going through your homework and study modules, you should have the chart handy so you can use it.